Okay, so hello everyone. I'm Sachin, and this is the first lecture or the prerequisite lecture on density operators. So, density operators are also commonly known as density matrices, and it is denoted by this rho hat T, and it is an alternative representation to a quantum system. So, in this case, we define the quantum system using a state vector psi of t in the Hilbert space H, and the dimensionality of the Hilbert space can be chosen to be n, so very generic. So, first question, why does one want to use density operators? If so, the question is this: why does one want to use density operators when you already have the state of your quantum system represented by the state vector psi of t in the Hilbert space? So, the answer to that, as we shall see in this lecture, is that it enables simple calculation of observables in mixed quantum systems. Now, an important keyword here, mixed quantum systems. So, what are mixed quantum systems? So, there's two types of quantum systems, pure and mixed quantum systems. So, in the case of a pure quantum system, which is denoted by psi of t, you have a single descriptor of the quantum system. Let's say psi of t. So this would be a pure quantum system. Now, when you consider a mixed quantum system, it generally is used to denote a statistical ensemble. These are the most common mixed quantum systems, or these are mixed quantum systems. So, mixed quantum systems are very useful for quantum statistical mechanics. So, let's just say you have a bunch or a distribution of pure quantum systems which you are studying. In that case, you would define that the complete system to be a mixed quantum system. So you can say that a mixed quantum system, you can think of a mixed quantum system as a bunch of pure quantum systems with certain probabilities to be found in that pure quantum system. So if you assume that your system is in thermal equilibrium, the probability of being found in a particular quantum system, or the probability of being found in a pure quantum system with energy, let's say E, would scale as a factor of exponential minus E over kbt, where kb is the Boltzmann constant and T is the temperature. Okay, so in this case, let's just say you have a decent temperature such that you have a distribution of quantum systems which you are studying. So in this distribution, the requisite or the complete system would be a mixed quantum system. So mixed quantum systems are often what you find in spectroscopic ensembles. So in spectroscopic ensembles, you generally have mixed quantum systems. So to motivate this, consider this example. So consider a particular vibrational transition. It would be easiest to explain this. And some finite temperature of the bath. So let's just say temperature is 300 Kelvin. So in this condition, let's just say a vibrational transition has some vibrational frequency which is in the orders of hundreds of wave numbers. So let's just say 500 wave numbers. So in this particular situation, your transition or your vibrational ground state will have a certain distribution in its so essentially a vibrational ground state will have a certain distribution in the vibrational states, which is given by, let's just say, your number states of your harmonic oscillator. So in such a scenario, let's just say you are probing that specific vibrational transition. So to describe that particular quantum system, which is a superposition of different vibrational number states, that state would be a mixed quantum state. And the probability of being found in different vibrational states sorry, is given by a certain Boltzmann factor. So this would be an example where where mixed quantum states would be extremely useful. So mixed quantum states are extremely useful in spectroscopy, and hence we will be using mixed quantum states to perform a lot of calculations, and hence the density operator formalism is necessary. So that's just the reason behind why we are using density operators instead of state gets in the Hilbert space. So now that we have described pure and mixed quantum states, let's start off with pure quantum states first. So the density operator for a pure quantum state is defined as the outer product of the state ket with its Hermitian conjugate, which would be the bra, and it is defined this way. Now, as I just mentioned, the density operators enable simplified calculation for observables in mixed quantum states. So let's start off by calculating the expectation value of an observable. Let's just call it A hat for this pure quantum state. So this is an operator A hat, corresponds to observable A. Let's just say that it has eigengets AI. The set of eigengets belongs to the Hilbert space H, and correspondingly you have eigenvalues AI, the set of eigenvalues. So it satisfies the eigenvalue equation. So A hat acting on AI will give you AI get AR. So for this specific observable, let us calculate its expectation. Let's just calculate its time dependent expectation value, which is given by bra psi of t A hat get psi of t, which is the conventional definition for the expectation of a particular observable. And of course, this is equivalent to psi A hat t psi, where this is just your Heisenberg operator, which is defined this way. So, if it has not been made clear just yet, in this lecture, we are considering the evolution of the quantum system, the time evolution of the quantum system with respect to some evolves in time with respect to some time independent Hamiltonian H0. So this time evolution operator is just the evolution operator with respect to the time independent Hamiltonian H0, which is just exponential I upon h bar H0 t then minus I upon h bar H0 t. So just to repeat again, in this lecture, we don't consider any time-dependent Hamiltonians. So the evolution of your quantum system and the which is described by the state get psi of t or rho of t, which is the density operator or the density matrix in a specific basis, is with respect to the time-independent Hamiltonian. So let's go ahead and perform this calculation, which is bra psi of t a hat ket psi of t. Now, I will be using the resolution of identity criteria. So I will insert an identity here, and then let's just say I define another set of basis states n, which belongs to the Hilbert space. So by doing so, what this gives me is bra psi of t. So this basis is complete, and the sum of the outer product of all the basis states would give you identity. So you squeeze this in here, and you proceed with the computation of the expectation value. So you can pull this summation out over all n, bra psi of t get n bra n a hat get psi of t. So both these terms are scalars. This is just simply the projection of psi of t on n, and you take a complex conjugate, and this is similar to a matrix element of A. So a matrix element of A in general would look something like this. So what I'm trying to motivate here is that both these quantities are scalars. So I can play around with their order. So I switch the order, I bring the right term to the left and the left term to the right. So by doing so, I will be able to perform a specific simplification. So here, if you notice, you have your density operator. So that's good. So I would rewrite this as n a hat times get psi of t bra psi of t. So I'm going to pull out the density operator acting on get n. So this is rho hat t for the pure quantum system defined, and then this gives you sum over n bra n a hat rho hat t get n. So what is this? Mathematically, this is the trace of the product of a hat t of a hat with rho hat t. So you take the product of the observable a hat with rho hat t and then sum along all its diagonal elements. So this is trace of a hat times rho hat t. Don't worry about the trace, it's a mathematical operation where you essentially just take the sum of all the elements which lie along the diagonal of the matrix. I will be talking about the trace in great detail soon, so nothing to worry about. This is also equivalent to the trace of A hat T rho. So in case 1, your quantum system evolves in time and your observable is static. And in case 2, your observable evolves in time but your quantum system is static. So the first case corresponds to something which is analogous to your Schrodinger picture for your state kets, and the second case corresponds to your Heisenberg picture which you learn for your simple state ket representation. So that's good. Now, since we have gotten to this point already, let me digress into the properties of the trace. Properties of trace. As I had just described, if you have a particular matrix, then the trace is just the sum of all the diagonal elements of that particular matrix. So I will be proving how you can go from here to here after I describe the properties of the trace. So the first property of the trace, it's the invariance to cyclic permutation. So what does that mean? Let's just say you take the trace of 3 operators, A hat, B hat, C hat. If I permute these 3 operators in a cyclic fashion, which means that if I move C hat here, then the trace remains the same. And of course, I could do another cyclic operation and move that here. So that would be this. So if I take the trace of the product of A hat, B hat, C hat, or C hat, A hat, B hat, or B hat, C hat, A hat, that should give you the same result. So how do we prove this? So consider the trace to be taken along some arbitrary basis. Let's just call this basis, let's just say n sub I. I'm sorry, I'm defining a lot of bases, but this belongs to H. And yeah, I had defined the dimensionality of the Hilbert space to be n2, so please just don't get confused. Too many terminologies, but let me call this basis n sub I. So you go from n1, n2, so on and so forth till nn. So now let's just take the trace of ABC, which would be in this n sub I basis, would be some n sub I, bra n sub I, A hat, B hat, C hat, n sub I. Now, again, here we will exploit the resolution of identity criteria. So I put in an identity and then I will just introduce another basis which is complete. Let's say m sub I. And what I get after that is something interesting. So you get n sub I, A hat, B hat, then put this in, m sub I, ket m sub I, bra m sub I, C n sub I. So this would be equal to, I can pull the summation out, n sub I, m sub I, the sum over both the indices n sub I and m sub I. So then I get this, bra ni, A hat, B hat, m sub I, bra m sub I, C hat, n sub I. Now, as you can see, for a lot of these proofs, what I'm just going to do is now I'm going to observe that this is a scalar. So this is just a matrix element of the product of the operators A hat, B hat. So it's a scalar. And then this is the matrix element of the operator C hat. So I'm going to switch its order. because they're just scalars. So they're like numbers 5 and 10. So 5 times 10 is equal to 10 times 5, something like that. So you get bra m sub I, c hat, n sub I, bra n sub I, a hat, b hat, m sub I. Now what I can do after this is take the summation for n sub I in. I will explain that to you very clearly now. So what I'm going to do is still keep the summation over m sub I outside. There are m sub I, c hat, acting on sum over n sub I, get n sub I, bra n sub I, acting on a hat, b hat, m sub I. So this again, according to the resolution of identity criteria, would be identity. So that would be sum over n sub I, bra m sub I, c hat, a hat, b hat, get m sub I. So which would be the trace of c hat, a hat, b hat. So we proved. Now, a question which would arise in your head would be, in the previous case, I wrote the trace of ABC at the beginning of the proof using basis n sub I. So n sub I, a hat, b hat, c hat. And now I'm writing the trace of c hat, a hat, b hat as the sum over m sub I, bra m sub I, c hat, a hat, b hat, m sub I. And then I claim that the trace of a hat, b hat, c hat is the same as the trace of c hat, a hat, b hat. So this leads to a very interesting property. So this would only be true, so the trace of a hat, b hat, c hat being equal to the trace of c hat, a hat, b hat, if the trace, which is the second property. Okay, so before I continue, please go on and prove that the trace of c hat, a hat, b hat is equal to the trace of b hat, c hat, a hat. So this is homework. Now, the trace of ABC being equal to the trace of CAB would only be true if the trace, the mathematical operation, is basis independent. What am I trying to say? The trace of ABC is taken with respect to the basis states n sub I, and the trace of CAB is taken with respect to the basis m sub I. And then I'm concluding that the trace of ABC is the same as the trace of CAB. So that must mean that this operation, m sum over m sub I, bra m sub I, c hat, a hat, b hat, get m sub I, is equal to the sum over n sub I, c hat, a hat, b hat, n sub I. So what does that mean? That must mean that the trace is basis independent. But I'm just making a random claim. So let me prove this, that the trace is basis independent. So let's start off with the LHS of the equation, the left hand side. So which is sum over all m sub I, bra m sub I, c hat, a hat, b hat, get m sub I. So now I'm going to introduce the resolution of identity criteria. So you can realize that all these proofs are very simple once you introduce the resolution of identity criteria. So that would be, and then I will introduce the basis n sub I states. I will introduce these states. And then I will do the same thing where this yields m sub I, where all m sub I and n sub I, bra m sub I, c hat, a hat, n sub I, n sub I, n sub I. Now, what you could do is bring this quantity here. So what you will get is sum over m sub I, n sub I, and n sub I, b hat, m sub I, m sub I, c hat, a hat, n sub I. So sum over n sub I, n sub I times b hat, and then you take the m sub I summation inside as I previously did, m sub I times c hat, a hat, n sub I. So this is identity, and then you get the sum over n sub I, n sub I, b hat, c hat, a hat, get n sub I. Now, let's do this again, where now you can, if you wish, you can put the resolution of identity here and then fill it up with m sub I. So what that would do in that case would make it sum over m sub I. You should try this out. M sub I times, so then this will come here, a hat, b hat, c hat times m sub I. So we started off with m sub I, c hat, a hat, b hat. So now we got to do this operation one last time. So you put the identity here, and then you use the basis n sub I in this case. So you get n sub I, n sub I. So once you do that, then you can move the c hat to the left. So in the end, you should try this out too. You get n sub I plus n sub I, c hat, a hat, b hat. So we started off with this. So we started off with the trace of CAB. Sorry. The trace of CAB, where the basis considered was the m sub I basis. And then you want to prove that this is equal to the case where you take the trace of CAB with respect to the n sub I basis, which we have done here. So this is proved. So what does this mean? This proof is a bit tricky, but what it ends up proving is that the trace is independent of the basis in which it is taken. So let me give you a quick summary of property 2. Quick summary. What does this mean? So what this means is, let's just say you have some operator. So the proof for property 2 would be much simpler if you just considered a single operator, but I considered all three operators. So a simple way to prove it would be to consider this: n sub I, n sub I, a hat, get n sub I is equal to, if you change the basis, m sub I, a hat, get m sub I. So this can be done very simply by putting in the resolution of identity and expanding it with the m sub I basis state, and then you get your result extremely quickly. But in this case, I had to play around with a bunch of mathematical manipulations, and only then I could prove that the trace base is independent, because I had three operators. So I had to do this, play around with the cycle. I had to move the terms around and so on and so forth to get the result. So the quick summary for property true would be that the trace of any operator, be it a simple operator or a product of a bunch of operators, you take a trace of an operator or a bunch of operators, it does not depend on the basis you consider. Okay, so that's a quick summary of property 2. So these two properties are the most critical ones, but then let's consider a third property, which is really not too important, but since it's given in various textbooks, I shall cover it too. The trace is invariant to unitary transformations of operators. What does that mean? Let's just say a unitary transformation is performed using some unitary operators, of course. So let's just say you want to transform some operator S. So the transformed operator would be U hat dagger S U hat, where these are some arbitrary unitary operator. So it's essentially just a rotation operation in the Hilbert space. So unitary operators are defined such that U hat dagger U hat is equal to identity, and this is also of course equal to U hat dagger, which to summarize very simply would be U hat dagger is equal to U hat inverse for unitary operators. So this is very simple matrices knowledge or very simple quantum mechanics knowledge. So how do you prove this? So the trace of what this means is the trace of S prime is the same as the trace of S, which means that the trace of U hat dagger S U is the same as the trace of S. This is quite obvious. So as I just mentioned, that the trace is invariant to cyclic permutations, which is the first property which we proved. So move this here, and then you get the trace of U hat dagger S. And then as mentioned using this property, this is just identity. So you get the trace of S. So the trace is invariant to any unitary transformation. So property 1 and 2 suffice. Property 3 is just a consequence of property 2. So we don't really need to digress into any other properties of the trace. So the main properties of the trace which need to be considered is that the trace is invariant to cyclic permutations, and the trace is independent of the basis, the set of states in the Hilbert space, which is the basis, and then the mathematical operation is independent of the basis which you consider. Okay, so this is good. We have summarized the properties of the trace in the process. Now, let's consider elements of the density operator. Just a recall. We are still considering pure states. I have not digressed into the statistical ensemble and the mixed states discussion yet. So now consider the elements of the density matrix, I should say in this case. So you take the density operator and consider a specific basis, so you get the elements of the density operator in that basis. So let's just use the basis n sub I. So u rho hat t, so now is get psi of t, bra psi of t. So the motivation behind considering the elements of the density matrix is that I want to give you guys a physical picture on what the diagonal and off diagonal terms mean. So that's why I'm considering the elements of the density matrix. And all the discussions which we do here are applicable to mixed states as well. So all our discussions for pure states are applicable and can be extended to mixed states. So better to have this discussion right here. So I'm considering the basis states, n sub I. So using the resolution of identity criteria, I insert an identity here first and an identity here, and then using the resolution of identity criteria, I expand in the basis n sub I. But of course, you have to use a different index for both of the expansions. So here I would use n sub I, and then here I can use n sub j. Right, so I get n sub I. I'm doing the mathematics really slowly, so let's just take some baby steps here, because I'm assuming you guys are still relatively new to this formalism. So sum over n sub j, outer products of n sub j. So this n sub I would form an inner product with the psi of t, and then this n sub j would form an inner product with the psi of t. And then I can pull the summations out. Sum over n sub I, n sub j, but so since this is a scalar, the resultant inner product, I'll pull it out to the front of the summation. N sub I get psi of t, bra psi of t, n sub j. So what is left? Get n sub I, bra n sub j. So what is this? The first term is just the projection of psi of t on n sub I. So I will call this c I t. And then this is just the projection of psi of t on n sub j, but the complex conjugate of that. So it's sum over n sub I, n sub j. I'll call this c n sub I t and c n sub j t instead of I and j. So this would be c n sub I t, c n sub j star t, get n sub I, n sub j. Okay, so this would be the element of a specific row corresponding to n sub I and column corresponding to n sub j. So let us analyze the diagonal terms first. So when n sub I is equal to n sub j, the element of the dense, okay, so let me call this row n sub I, n sub j t. So this is the, as I just mentioned, the element of the density operator corresponding to the row which describes n sub I and the column which describes n sub j. So when you consider the diagonal term, row nit would be equal to CNIT, CNIT star, which is just modulus CNIT square. Now, something which is important to note is that these are just the coefficients of the state get onto various spaces states. So CNIT is just the projection of psi on Ni, and this is just the projection of psi on Nj, and then you take the complex conjugate. So the idea behind this is that if you take a modulus square of the prefactors or the basically the coefficients of the state ket psi of t, they will be time independent when you take this modulus square, so which is equal to CNI square, because essentially these coefficients will, let's just say that they would take on the form CNI e raised to the power minus I e n I t over h bar. And when they do, and you take the modulus square of this, you get this. This is how the coefficients evolve in time, but we will not digress into that because that's simple time independent quantum mechanics. So now let us discuss the off-diagonal terms. In this case, n sub I will not be equal to n sub j. So rho ni nj as a function of time will just be CNIT CNI nj star t. I will explain the physical meaning of the diagonal and the off-diagonal terms soon. So, but let's just complete the mathematics first. So in this case, this term time independence will evolve as such, so e raised to power minus I e n I t upon h bar c n I, and then this one would be as e raised to the power positive I, because you're taking the complex in this case it would be the complex conjugate of this quantity, so e n j t over h bar c n j star. So the time dependence of these coefficients is contained in these e raised to the power something terms. So what that would mean would be CNI CNJ star e raised to the power minus I omega ni nj where omega ni nj would be e ni minus e nj over h bar. Okay, so let's talk about the diagonal terms first. So all the diagonal terms, so let's just say the first diagonal element in this density matrix, which would be rho n1 n1, would be mod c n1 square, which is essentially this is n1 get psi t squared. So it's essentially the probability of the quantum system being found in state n1. So this is applicable for every ni. So the diagonal terms of the density matrix are populations, and as is evident that your quantum system needs to be found in at least one, it needs to be found in at least one of the states. So the sum of all the probabilities would be 1. So which is known sum over all, let's just say, n sub I c square would be 1, which is the case that the sum of all the probabilities of the quantum system being found in different states is 1. So what that also means is that the trace of the density operator is 1. Okay, so now let us discuss the properties of the off-diagonal density matrix terms. So let's just consider the general off-diagonal element which we have, which I will just jot down from above. Rho ni and j is c ni c n j star e raised to power minus I omega ni n j t. So these are known as coherence terms, which oscillate at a frequency given by the difference in energies of the ni and nj state, which I shall again jot down again. Ni minus e nj over h bar. So if you have a coherent superposition, why are these called coherences? Because if you have a coherent superposition of two states, let's just say your quantum system is a coherent superposition of two states, ni and nj, then the time dependent coefficients of the states ni and nj, when you take a product of the two, they oscillate with this frequency, and hence these states are referred to as coherent states. So as a homework, I would urge you to consider a quantum system. You can call it any arbitrary quantum system, but let's just say you consider the same thing, psi of t, and then it has some coefficient c nit, get ni plus c njt, get nj, and you calculate c nit, c njt, and take a product of the two and see that it exactly matches this, which is very obvious and very simple to see, but you should try this out as a simple exercise for homework. So just to summarize whatever we have learned, the diagonal terms of the density matrix in any arbitrary basis, these terms, they represent populations, and the sum of all the diagonal terms is equal to 1. So that's the trace. Now, the second thing to be considered is these off diagonal terms. So I'm not doing a good job at drawing these, but these off diagonal terms are known as coherences, and the diagonal terms that I just mentioned are populations. So you have some physical significance for the diagonal and off diagonal terms of the density operator. So that's good. Now let's continue with our discussion. So as of now, let us discuss two properties of the density operator. The third property will come once I explain the density operator of the mixed state. So as of now, let's just consider these two properties. Call it alpha, that the density operator is Hermitian. This should be quite obvious using the definition of the density operator, which is just the outer product of the state vector with its Hermitian conjugate. So you take the Hermitian conjugate of this will come here, and this will go here, and then you have to take the Hermitian conjugate. Okay, so I might have not been extremely clear with this, but the Hermitian conjugate of, let's just say, two operators, or could be kets, would be dagger. So you reverse the order and you take the Hermitian conjugate. So what that would mean is psi of t times ket psi of t, and you have to take the Hermitian conjugate. What that would give you is ket psi of t psi of t, which is just equal to rho hat. So of course it's Hermitian. Another way to prove this, which is just more mathematically rigorous, is to consider the density operator in a specific basis. So that would give you, let's just consider the previous case where we wrote the elements of the density operator in a specific basis, which would I am referring to this. So let's just write it this way. Suppose n sub I, n sub j, c n sub I t, c n sub j t, ket n sub I, sorry this is star here, bra n sub j. I just want to ensure that I've copied it correctly. Yes, okay, so that's good. So you can derive this the same way as I have previously, using the resolution of identity criteria. So now you take a Hermitian conjugate of this expression. So it's very easy to observe that that would be c n sub I t star, c n sub j t star, and then you will get ket n sub j bra n sub I. You should go and verify this. Verify. It's homework. So another thing which I can do is, since n sub I and n sub j are just dummy indices over which I'm doing the summation, I can interchange n sub I and n sub j. Sorry, there will not be any complex conjugate there. So I can interchange the indices n sub I and n sub j. What I mean is just change this from n sub I to n sub j, and from this from n sub j to n sub I, and so on and so forth. That would make it c n sub j star t. Sorry, this would be c. Sorry, I'm messing this up. This would be c n sub I t, c n sub j t star, n sub I, n sub j. So this from here to here is just swapping the indices n sub I and n sub j within the summations, which is a valid mathematical operation because they're just dummy indices which are used for the summation. And you can observe that this is the same as rho hat. I should put in, this is all rho hat t. So rho hat here is just the same as rho hat t. Okay, so this is a more mathematically rigorous proof for the hermiticity of the density operator. Now, let's just consider property 2, which I shall call beta. Right, and that is that the trace of the density operator is 1 because the diagonal terms indicate populations, and the quantum system must be found in one of the particular what do I say? The quantum system must be found in one of the particular states, right? So the sum of all the populations would add up to 1. So these are the two properties of the density operator which I would like to consider till this point. Now let's continue. And now we are back to mixed states. Now we have to consider mixed states, and this is the entire idea of this class. Why are we using density operators? We are using density operators because they're useful in calculating the value of observables in a mixed quantum system. So let's continue with that discussion. So we're almost close to the end of this class. So it should be about 10 more minutes and then we should be done. So now, mixed quantum systems. So a mixed quantum system, as I just mentioned, is just a statistical ensemble. It's essentially used to describe systems where we have incomplete information on the system itself. So let's just say that you have a pure system, let's just call it psi 1t, and the probability of finding it would be p1, and another system psi 2t, and then the probability of it existing would be p2, and so on and so forth, and then you have psi and t with the probability of it being found being pn. So these probabilities in general depend on the temperature of the system, but yeah, let's not digress too much into the Boltzmann distribution and thermal equilibrium and non-thermal equilibrium conditions, so we're not really considering that. So this rho in this case would just be the sum over all, let's just say k, of p, would be pk ket psi kt pra psi kt. So you can observe in this case that this is the density operator of a mixed quantum system, which is just the sum of density operators of the pure quantum states weighted by the probability of the state being found. Right. And again, here the sum of all the probabilities. One moment. The sum of all the probabilities would be 1. So this is a particular criteria, and all the probabilities, of course, would be greater than equal to 0. You cannot have negative probabilities, that is obvious. Okay, so these are the two criteria for this particular probability coefficient. So for mixed quantum states, the density operator can be described as such. It is just a statistical average of the density operators of the various pure quantum states. So I'll call this rho k. And this probability generally depends on thermal considerations. And if you're in thermal equilibrium, these are in thermal equilibrium dictated by Boltzmann distribution or factors. Okay, so that's good. So you can describe this statistical ensemble using the density operator. So now, and all these vectors, psi k t, this set of quantum systems, they belong to the same Hilbert space. That is good to mention. So now, the selling point to this is that when you calculate the expectation of the same observable A, which is in the Hilbert space, you can do it using trace of E hat rho hat t, or equivalently the trace of E hat t rho hat, which I haven't proved to you guys. I intended on proving it in the pure state case itself, but we can prove this here using the properties which we have previously defined. So we have two proofs now. One is to prove this, and number two would be to prove that this relation holds in the case of the mixed quantum state as well. But as of now, just believe me that this relation is true. So we go around full circle. So our entire class is quite self-consistent, that the entire idea of using these density operators, it allows for the easy calculation of the expectation values of observables in the mixed quantum state. So let's just say you have an observable A. You take a trace with the density operator of the mixed quantum state, and then you get the expectation value. It's a very simple calculation. But now, let's think of how to prove it. So proof for mixed quantum state. So now let's think about it carefully. So if I would want to calculate the expectation value of observable A, I would first consider the probability of the quantum system being found in that particular pure state. So let's just say that you have n pure states, right? So the probability of being found in that particular pure state K times the expectation of the observable in the state K. I hope this is clear. So you're calculating the expectation of the observable. Calculate expectation of observable in pure state psi k, and multiply it with the probability of being found in state psi kt. Probability of your quantum system being found in the state psi kt, and then you sum over all k, and then you get the expectation of the observable A. If this is not clear to you, please think about it more carefully. So now, what I will do in this situation to prove the case is again just introduce some basis. Let's just say n using the resolution of identity criteria. Okay, psi kt e hat psi kt. So now introduce the resolution of identity here and expand it in some basis n. And now this, as I'm repeating this again, but n belongs to this Hilbert space again. So what you get is sum over n and k, where the k indices are for the quantum systems, and n is just a basis which I have introduced. So pk bra psi kt get n bra n a hat get psi kt. Here I have pulled the summation over all n, which is here outside, which is quite obvious by now. So I just did that implicitly without mentioning it. So now again, I interchange the terms as I have done previously. So you get sum over n and k, p, k, bra n, because they're scalars. That's why I'm interchanging the terms. Psi kt, bra psi kt, get n again. So I can move the summation with respect to k inside now. So look at the way I do this. This is just a mathematical manipulation but please look at it very carefully. So I will move this summation over k inside. I get pk get psi kt pra psi kt, and then this will act on ket n. Again, this is just your density operator, which is equal to the summation over n pra n a hat rho hat t ket n. So this is equal to the trace of a hat and rho hat t, the product of a hat and rho hat t, which is equivalent to the trace of a hat t rho hat, which I was supposed to prove for the pure state case, but I did not, so I will prove it here. So proof for trace of a hat rho hat t being equal to the trace of a hat t rho hat. Before I proceed, let us investigate quickly the structure of rho hat t. So I'm just going to be doing it for the mixed quantum system case, which is more generic than the pure quantum system case, because if we set k, so let's just say I sum over k, pk get psi kt pra psi kt, and then if I set t to 1, then the probability of being found in that particular state would be 1, and then you just have a pure state, right? So the mixed quantum system proof is always more generic and is applicable to the pure quantum state case. So let us investigate the structure of this a bit carefully. So this psi kt can be written in terms of a time evolution operator and a stationary state psi k. So I will do that. U hat 0 times get psi k. Again, the evolutions in this case are considered only with respect to a time independent Hamiltonian in this lecture. This will just be U hat dagger pra psi k. I'm just taking the Hermitian conjugate of the first expression and inserting it into the right hand side of this equation, and that this will be equal to, I can take the U hat t and the U hat dagger t out of the summation over k, because it doesn't have any dependence on which quantum system it is evolving. So sum over k, pk get psi k psi k acting on, and then this U hat dagger t acting on this, and then this is just your density operator for the mixed quantum system, which is independent of time. So it takes on this structure. So now something which is really important to observe about the evolution of the density operator, which is different from the time dependent evolution of different operators or observables, is that consider some random operator a hat t. Its evolution or its time dependence is described this way, if you remember. Again, this is just the Heisenberg operator. And so you can observe the difference in structure. So the time evolution of the density operator is U hat rho U hat dagger. I apologize for this. And then the time evolution of any other operator is given by U hat dagger a U hat. So it's a switch. So this is something which you should be careful about, and it's important to note. Anyways, so this is the structure of rho hat t. So let's just put it in the expression. So trace of a hat rho hat t, and then you want to prove that this is equal to the trace of a hat t rho hat. So let's just put the expression for the time dependent density operator here. You get a hat U hat 0 t rho hat you had dagger T. Now you can move this here, and then you get U hat dagger T, A hat, U hat T times rho. And then this is again, as I just mentioned, A hat T. So it is equal to, I apologize for the carelessness, this is trace. Then you get the trace of A hat T rho. So that proves what I previously mentioned, that the two situations are equivalent. In one case, your quantum system evolves in time, your operator is stationary. In the other case, your quantum system is stationary and your operator evolves in time. Both these situations should be equivalent. So we have proved what we set out to prove. So in conclusion, the expectation of some observable A in a mixed quantum system holds the same result as it does for a pure quantum system and is given as the trace of A rho hat T or trace A hat T rho. Just a word of caution, these terms can be exchanged because of the cyclic permutation invariance of the trace. So don't be surprised if various sources mention it in the opposite direction. So that concludes that proof. And to conclude this lecture, let us talk about property 3, which I intended on describing once I introduced mixed quantum systems to you guys. So I introduced alpha and beta previously, this is gamma, and which says that the trace of rho square is equal to 1 for a pure quantum system and is always less than 1 for a mixed quantum system.